Hello, welcome everyone after the lunch. So we will have two talks in this session. First, Professor Nirmal Viswanathan will be talking about topological effects due to reflection of light beam at a dielectric interface. Professor Nirmal Viswanathan is from University of Hyderabad.
I should first thank Professor Dutta Gupta and Tarak for organizing this meeting and also inviting me. And the first mail I got within 5 minutes, 10 minutes, I said I am coming. So it was that eager I was. Thanks for that. And thanks for the nice audience. And we will look at some interesting effects. We have been listening to a lot of fancy things about light in the last couple of days. What are all the things it can do and what you can do with light, what light can do to material, all the things. And if you think about it a little bit, and most of those methods and techniques that people were using required more or less little more expensive equipments like tweezers and nanowires, nanoparticles, all things. I come from university. I should say that we don't have much of funds, though I shouldn't say that. But I want to make a story out of that. But even with less money, you can do some fancy things because light is still being explored and a lot of new things are coming up. So in this talk, I'm going to take you guys back to a place where if you look at Born and Wolf book, for example, or any optics book, the first chapter more or less will talk about the reflection of light at a dielectric interface. And the first thing that they will do is Fresnel reflection coefficient. So I've given a diagram here to get started. So you have a dielectric interface, N1 and N2, standard classic electromagnetic theory problem. So we'll take this to be air and this to be glass, and a ray of light is going and gets reflected. And because we have always been told that light is a plane wave and it does rectilinear propagation, we will say that this is a plane wave that is going. So that means that a plane wave is going, and this is lambda, like somebody else has mentioned. And we will give an electromagnetic character for that. So you have an electric field and you have a k vector associated with that, and then it goes and gets reflected. It also, part of it gets transmitted, so we will not worry about it because whatever happens in reflection, complementary is going to happen in transmission because I'm going to consider a lossless kind of a situation. And the parameters that I am going to have in control through this talk is that I have a control on the angle of incidence. That means I can go from 0 degree, which is normal incidence, all the way to 90 degrees. And I'm going to change the polarization characteristics of the light that I'm sending in. So I'm defining it by two parameters. One is theta e and one is phi e. Theta e is basically, if you look at it, cut a plane here and then look at the electric field vector, you have x and y component, and the angle that the electric field vector makes with reference to the x-axis is my theta e. And if there is going to be a phase difference between the x and y components, that is going to be phi e. To give you an example, if it is theta e is 45 degrees and phi e is 90, you will get a circularly polarized light. And it goes in, gets reflected, and then comes back. And I put a gadget here. This box, hatched box, is I put some device polarization manipulation elements to change these two parameters. And I put a device or a couple of devices here to make a measurement on what are the changes that is going to happen for the beam that is going to get reflected. There is nothing new. It's a standard classical electromagnetic theory problem, but still there is something left out in all these textbooks, and we are going to discuss about that. So I'm going to show you a couple of videos to start the session. So if you look at it here, theta I, which is the angle of incidence for the light that I'm sending in, is 45. That means this theta I is 45. And the theta E, I was telling that if it is 45 and pi by 2, it is circularly polarized light. So I'm giving some 16.28 degrees. And you will see that I'm going to change this, fixing this. And what you're seeing here is a polarization map of the light that is going to get reflected at this dielectric interface. And all these green color circles represent polarization or state of polarization at different points in the beam cross section. And all these purple color lines are what we call as stream lines to track how the polarization or the major axis of the polarization ellipse changes in the cross section of the beam. And I'm going to run this parameter and see what is going to happen. And this is going to be basically the intensity of one of the circular polarization components of the light that I'm going to get reflected from this one. This is orthogonal to what I'm sending in. So you're looking at it in the orthogonal component of it. And this is the total intensity and the total polarization change that is going to be measured in the beam cross section. Yeah.
You are talking in Gaussian beam or plane wave?
Not a plane wave.
Gaussian beam.
It's a Gaussian beam and it is a weakly diverging Gaussian beam. So as you said, thanks for reminding, you already made a comment yesterday saying that Gaussian beam, no, that is what we all learned. What I'm going to tell you is what we have not learned. So you said that Gaussian beam is intrinsically inhomogeneously polarized, and I'm going to exploit that and say that there are certain interesting things that are going to happen. So I'm going to run both the movies parallelly. You can see that as I change this parameter, the intensity of one of the polarization components is changing. You can see that the beam is shifting. It is becoming close to a donut mode, and then it kind of shifts to the other part of it. And these are all in millimeters. And you can see that the polarization in the cross section of the beam is also changing quite dramatically. This is just a reflection at a dielectric interface that we are looking at. I will run one more video where I have two parameters. Now I have angle of incidence and I have the polarization ellipse angle. I'm starting with normal incidence and getting reflected, and I'm going to change these two parameters, and you will see what is going to happen to the cross section of the beam as we run these two parameters. I'm changing this and also changing the angle of incidence. You see that dramatic change. You will see that it is evolving still, and of course the intensity is dropping down, and you will see that
You are detecting only circular polarization component.
I am measuring total field and I am plotting it. Here you see that at some point the polarization in the beam cross section dramatically changes, and then it kind of pushes and then becomes. So these are the pattern that Senthil in the morning and earlier Nirmalya also was telling that these are the lemon kind of polarization pattern that you see in the beam cross section. So now you can see that by changing the angle of incidence from 0 to close to 90 degrees and changing the polarization ellipse of the beam that I'm sending in, you can change the reflected component even from a simple dielectric interface of air glass changes quite dramatically. So the question is that why didn't we know about all these things, and what is it that is going on as far as these kind of systems are concerned, and that is going to be the main aspect of my talk. So little more details than what I have given here. So I have a laser which is helium neon laser, and I have two lenses here to make sure that I have reasonably collimated the beam because laser beam intrinsically diverges, and I put a polarization components here, half-wave plate, a polarizer and a quarter-wave plate to manipulate the state of polarization of the light that is going in. And I put a lens here of focal length -5, it is a concave lens, so I am weakly diverging the beam. This is only a convenience for me to model and then show the effects. And this is the angle of incidence, angle of reflection, and I put another lens here, this is L2, focal length is 12.5, I adjust the distances so that after this L2, the beam comes back collimated. I put a quarter-wave plate and a polarizer to measure the Stokes parameters of the light, and I have a camera here to capture all the intensity images and then convert them into state of polarization in the beam cross section. So whatever we are going to talk about is all described in detail in these papers. And so whatever images or the movies that I showed in the last two slides basically comes from this kind of an experimental setup. So a quick recap of what we have seen. So these are the polarization pattern and the intensity in the beam cross section that we have seen. in different for different conditions. You have to remember that this pattern happens at the Brewster angle. We'll come back to it in a little more detail at a later point of time, and this corresponds to TM polarized light. And what was surprising for us is that when we looked at the phase structure of this, we saw that this is the kind of intensity profile, and the phase structure showed a helical pattern. So a simple reflection at a glass interface already has a vortex hiding behind it. So that is the point that I want to kind of emphasize, that then kind of things open up in a little more nicer way once we kind of make sure that this is understood. More details I will show. This is just a snapshot of what we are looking at. So, introduction. So the reflection and transmission that we have all looked at so far, it considers that it is an ideal electromagnetic plane wave, and the interface that we are looking at is an isotropic dielectric interface. Typically it is an air glass, and it is one of the fundamental problems of electromagnetic theory or electromagnetic optics. So this is the system that I have already done, and all the parameters of interest are already mentioned there. But it's an ideal situation, but none of the laser beams that we use ever going to follow this kind of an ideal situation, so we cannot use the same Fresnel formalism and then find out that what is going to happen to the polarization. So you have to develop a real model for an optical beam, meaning that it is diverging, and there are a lot of other things that are happening, and then we do it by decomposing into several different plane waves, as is shown here. So you can see that lens weakly diverging gets reflected, one more lens, it gets collimated. So you need a different kind of a model to look at all kinds of changes that are happening in a simple reflection process. So what we do is that we are kind of associating for every direction one k vector, and what are all the things that are changing along with that. Essentially what it means is that if you focus it, you are going to have a non-point like source in the image space or in the momentum space, right? So that is one thing that we will have to keep in mind, though we all say that we start with a point source. That is not going to be the reality in when you start doing experiments with these things. And step back again to kind of quickly recap. So this is the reflection at a dielectric interface, what we have been taught. So you have an incident light, reflected light, transmitted light. So these are the angles, and this is what we have been told, that external reflection is what I'm looking at, meaning that the refractive index of the first medium is less than that of the second, and this is for TE polarization. It is going to change like this. For TM polarization, you are going to have a dip, almost null intensity at a particular angle, and that is your Brewster angle. And more important than that is that you are going to have a phase flip around the Brewster angle from 0 to pi or pi to 0, depending on the convention that one uses. Whereas for the other case, the phase in the beam cross section remains almost the same. And this is your complex amplitude that one can derive to see that how the reflection coefficient for two orthogonal components is going to depend on the angle of incidence and the refractive indices of the two interfaces. So I'm going to reintroduce the problem to make it convenient for what we have, what I had showed already. And this is the kind of diagram for that. So I take a plane wave here, ideally, and I put a lens. Yeah.
Did you look at the videos when you have from denser medium to lighter medium?
One more PhD, sir. We have not done it.
A set of videos for denser medium to lighter medium when you have the total internal reflection. Yeah. Because when you have total internal reflection beyond the Brewster angle, there's a bump in the phase.
Situation is much more complicated. I'm not going to talk. No. All those shifts I'm going to show here itself. I'm doing from lesser to higher. You are saying higher to lower. Yeah, I am not looking at it because mathematics is little more complicated. No, I said that. Because the mathematics is little more complicated because we have developed a model from basic electromagnetic theory. Right, so. That is the problem. We never consider that into any account, right? So I am calculating the divergence. I am giving you here 0.7 degrees. Every laser diverges more than this. But we never take it into consideration. But if you consider that and develop a proper model, all the images that I had showed earlier is already going to happen.
All the angle of spectrum representation they take into account. That we are deviating.
I have not seen any result which shows what I am showing, which means that people have not looked at it, or maybe they knew about it, they never bothered about it. All I'm saying is that these kind of patterns have never been reported, and that is why PRA is accepted. Right? So I have not seen this kind of polarization variation. Yes, Senthil, you had a question.
Yeah, I think mostly they talk about the frontal reflection, not the variation in the angle.
But that is the most important thing. That is the most important thing, right? You have to take that into consideration in these kind of situations. Okay, so now we will reintroduce, saying that we are not going to look at it as a plane wave situation or ignore the divergence that is already there in any laser beam, and then we will resolve each one of these real beam into an ideal plane wave and look at the reflection and transmission coefficient. In the process, what happens, as Senthil was telling, that you have a range of k vectors falling on the interface, and because of that, there is going to be a spatial dispersion of the Fresnel reflection coefficient that has to be considered when you are looking at these kind of a problem. And because of that, the angle of incidence at each one of these positions, even if you are looking at it as a diverging beam, is going to be different, and as a result of which, there is going to be a azimuthal variation in the phase that is going to happen in this situation. So because of that, if you take the reflection and transmission coefficient matrices in these kind of optical systems, you are going to have a very, very complicated system, which means that you are going to have a distorted and complicated reflection and transmission field profiles you are going to have, and the centroids of these positions or of these intensities is going to be shifted away from the geometric optics positions. And if you put them all together, you can think of Gauss-Hansen shift, Embed-Fedorov shift, transverse longitudinal spin shifts, and whatnot. All kinds of things are just waiting there to be unearthed. It is already there, and we have not seen it so far. Right? So that is basically what my talk is going to give details. So we'll step back and look at a generalized formalism to readdress the fundamental problem of reflection and transmission coefficients. And we'll take this beam that is coming in as a complex optical wave beam at a planar dielectric interface. And the method we have developed it, I will just give you a brief introduction to the formalism that we have developed. But it is, you can kind of argue saying that it is physically equivalent to a Fresnel formalism or Fourier decomposition method, but there is a lot more hidden inside that which has not been looked at so far. So basic idea is to get a complete 3D field information of the light that is going to be reflected and that is going to be incident on the interface. And the main thing is that you have to keep the geometric phase accumulated and the wavefront curvature information intact to extract all that information that is already hidden inside. So we will mostly look at Gaussian beam model, though we will say that this kind of a formalism that we have developed is applicable for any other wavefront that one can think of, including helical wavefront. So this is my problem. I'm kind of looking at it again, and I'm taking a Gaussian amplitude vector profile. So we can see that this phi e is already there between the x and y components, and I also have a theta e, which will tell me what is the electric field vector orientation of that. If this phi e is pi by 2 and this theta e is 45, you will get a circularly polarized light. You have a Gaussian beam envelope, and this is the k vector of the wave that is going in. So after the lens, the beam is diverging because that is the lens that we put, and then so we write down the electric field after the lens, and then you can see that there are rotation matrices, and this is the input electric field, and this is the electric field which contains all the information after the lens, which is so that it is diverging, but it also contains all the polarization information telling that the state of polarization in the beam cross section is varying, and this is the kind of model that one can think of for such a situation. phase. You can also put the phase for the field that is going in. And after the reflection, we kind of, this is the reflected field, and this is the k vector of the reflected light that is coming in, and we will collimate that information to measure it. So in a nutshell, this is the formalism that we have developed, and this is the matrix method, which has the phase, amplitude, polarization, all the information that you need about the beam. And this paper has all the details. It's about 20-page paper, and all the other information that one needs is already there in this one. Moving ahead, so we are going to take that equation that I showed earlier, and we will start simulating it. So for simulation, these are the parameters that we use. We use a helium neon wavelength, N1, N2 was given here. We've taken a nominal power of 1 milliwatt, and this I already said, theta E and phi E, and we have taken a beam waist of about 7 millimeters, and these two angle of incidence is 45, and weakly diverging lens. I already gave the divergence of such a beam that we are going to have. So these are the simulated results that we have. So the first line here contains all the input beam information. The second is reflected, and the third is transmitted. So you can see here that the total field is circularly polarized. That's what I'm sending in. So this is the x and y components of that field, and this is the phase information of the beam, of the Gaussian beam that is coming in. So once you reflect it with this kind of parameters, you can see that the x and y components have become distorted, both the intensity and the electric field. And please note that in all these diagrams, this white dot basically corresponds to the fact that that is the tip of the electric field vector that one is looking at. And you put them together, you see that the polarization in the cross section of the reflected beam is already distorted quite a bit. It has become elliptically polarized, and it is changing spatially quite dramatically. So you can extract the phase information from the beam cross section, and of course this is the transmitted beam information, which is basically complementary of this. Put them together, you will get this one, because we are looking at as a lossless medium. So this is the first information that we extracted from the model that has been developed, but it is the changes that one can see here in the simulation is very, very small. So one can always argue that, oh, it could be some error, mistake, all kinds of things. So how do we kind of amplify that? We will come to that in the next set of measurements. So this basically tells you that you have created an inhomogeneously polarized beam simply by reflecting a Gaussian beam of uniformly polarized light. And this is coming because of the fact that the Fresnel coefficients is different at different places. Yeah. Yeah, that's what I'm saying, because transmitted light intensity is more, right? So you always see larger effects in reflection because the reflection amplitude is very small. So you don't get to see that difference. Well, it's okay, but it is still there. We will see it as we move forward. Whenever you want to see small changes, it is always better to measure it in reflection because your amplitudes are very small. You can see larger changes that are happening in this one, right? So you have a complicated reflected and transmission profiles in this coming because of this reflection, and the only way to amplify is these kind of small effects is to go through a phase transition or a phase flip, and we saw that Brewster angle gives the right place for us to exercise that. So we went ahead and did this. So what we do now is that we go and sit around this Brewster angle or at Brewster angle, but because your beam is already diverging, around the Brewster angle there is going to be a angle Fresnel reflection coefficients which are not going to go to 0 like here. That is the point region that I have marked by this circle, and you can also see that the phase is going to vary in the cross section of the beam. And this is what we get. I already showed this. So you can see that at this point is your Brewster angle, but around this, because of your k vector variation in the beam cross section, you are going to have a small variation in the beam intensity and the corresponding change in the polarization state in the beam cross section also. It is, one can say that it is weakly a V-point singularity that one would talk about, or Senthil mentioned in the morning, but slightly distorted, but doesn't matter. Nevertheless, this kind of pattern does exist when you look at this experiment in the Brewster angle. So we did this single slit diffraction experiment to show that yes, it is not just a dark spot, but it also has an orbital angular momentum by showing that this interference fringe or the diffraction fringe that you see here basically splits here, and then you see this. It's a signature that the beam there carries angular momentum and hence phase singularity at the center. And you can also see that if you look at the total intensity, the earlier intensity that I said is for TM, but if you send a circularly polarized light, you see that all kinds of polarization components are there in the beam cross section. So one can see that this is a C-point singularity of one kind, this is a C-point singularity of another kind, and this is the L-line singularity. All kinds of polarization singularities are already present if you reflect the beam at the Brewster angle. And the only advantage is that it is magnified because the phase change happens so dramatically in the cross section of the beam. Yeah. Yes, Pawan. Glass. All kinds of things happen. Another talk, some other day. I am not even talking about all these things. We have done some of them. We have know what is going on. All kinds of things happen. All kinds of things happen. Yeah. Say that again. Of course. Yeah. I did not answer it completely because I didn't want to go into that direction, because one has to worry about too many things at that point, the substrate effects and all kinds of other things. Yes, I agree. Yeah, thanks for that. Yeah, it's a dispersion effect that one is looking at. Yeah. And okay, so now from the pattern that I showed earlier, you simply send the pattern through a halfway plate. You get a whole second generation of patterns. So if you see that previous one was 2 lemons were there, now you have 2 star patterns in the beam cross section. I've simply flipped the phase by sending it through a halfway plate. So this is at the Brewster angle, and you see that hyperbolic kind of a pattern, and you see a star and you see a lemon. All kinds of patterns happen, even either as in pairs or alone. All those things can happen by simply changing the angle of incidence and the polarization of the light that I'm sending in. So we have extracted the phase from the beam cross section. All of them show that there is a singularity that is present. The only thing is that in these 2 cases, the polarization singularity is slightly shifted, corresponding one to this C point and one is that C point, which tells you that there are 2 vortices sitting at the background of these polarization structure that one has, and these 2 has one orbital angular momentum or the phase change of 2 pi around the beam cross section. Now, we asked ourselves the question, is this situation very unique to a Brewster angle, or can it happen in any other angle? So meaning that the one thing that is always has to be kept in mind is that the wave vector and polarization is coupled in electromagnetic waves. We unfortunately don't treat them as coupled. So when you look at it as a coupled thing, it means that if you change the angle of incidence, the polarization in the beam cross section has to change. Or if you change the polarization in the beam cross section, the K vector will change. So this is a non-separable aspect of it. So that is what we brought in here to look at the reflection as a generic reflection process, to say that this kind of effects can happen at any angle of incidence. It doesn't have to be a Brewster angle. So we kind of moved ahead and then say that we have to configure this beam or the conditions at which we do this simulation and the experiment. By the way, I'm showing mostly simulation results, but we have experimental results for all of them. All of them are published in these papers. So we take a beam and then reflect it, same thing, but we, instead of looking at it as a particular angle, we kind of open it up and say that, can we look at this at any other angle or any other state of polarization in the Brewster, other than the Brewster angle. And this kind of allows you to look at all these beam shifts, Goussans and Imbert-Fedorov spin, all kinds of things are happening. people who are working in this area already know that all these things are manifestations of a larger phenomena which is known as spin-orbit interaction of light. Yeah. Separations are there, meaning? The one that I showed earlier. Okay. Now you have to refer to Senthil's paper. We'll talk about it separately. Right? It is a very simple experiment. You put this single slit in the beam cross section. Because the mode is rotating like this, you will see that the top part of the mode and the bottom part of the mode gets twisted. And then you see that instead of a straight diffraction line, you will see that the broken diffraction line, which has separation between them. Yeah. Many people have done these things. Yes. I am sending Gaussian beam with a diverging wavefront. After reflection. That is what I'm saying. Yeah. Weird. But what do? We've done experiments and showed that it. Huh? Zero. Spin angular momentum is there. But in the process of reflection, you have converted part of it into orbital angular momentum. Of course, you can kind of work. I'll show later on that the total angular momentum is conserved and all those things are taken care. Yeah. Right. So we look at this reflection as a generic process. So this theta e and phi e comes in. So we define two other parameters of the similar type to make sure that if this phi polarization parameters of the beam that I'm sending in satisfies these two conditions, then not only at the Brewster angle, I can make sure that this kind of a dip happens at any other angle of incidence. X-axis is angle of incidence and y-axis is theta ES. So that is what we have done. So we configure the experimental system in such a way that this reflection coefficient goes to 0 depending on what is the kind of ellipticity in the beam that you are putting in, the one that is going in to the interface. So this is what we have done. So you can see here that angle of incidence is 45, theta E is 17.8. This is your Brewster angle. And this is at some other angle, theta I is 70 degrees and theta E is 20.7. So this is what I was telling. There is a non-separability as far as the wave vector or the distribution of your wavefront and the polarization in the beam cross-section comes in and says that I can generate this kind of polarization pattern. Once you have these kind of patterns, it implicitly tells you that in the orthogonal component, there is a vortex which is hidden behind it that is already known for people working in this area. So I don't have to worry about getting this kind of a pattern only in at Brewster angle. I can get this at any other angle. So that generalizes the reflection process. And of course, we have extracted this phase. And of course, the single slit diffraction pattern is also shown. And okay, so this again emphasizes these things, which shows that the beam cross-section intensity changes quite dramatically. All these are spin shifts in the longitudinal direction. We can show that it happens in the transverse direction also. All these are at various angles other than the Brewster angle. And of course, we can calculate the Gauss-Hansen shift. This is the average beam shift along the x-axis as a function of angle of incidence. And I can vary the ellipticity angle. I can measure the spin shift of the plus and minus components of it. And then I can get this spin shift in the different directions in the beam cross-section. So these are all already there in the beam that I have generated by reflecting it at a dielectric interface. So now it takes us to the last situation. Now what happens if you have a normal incidence? So we have done it at any angle of incidence. Now normal incidence is a tricky process because it is a degenerate case where you have this beam that is going in, and then we put all these components here to like earlier, and then we say that at this place the wavefront is curved like this, and then you have the polarization that is varying, and these are the parameters that we have used. You can see that the divergence angle is still about 3 degrees or so. Everything is paraxial. that is the beauty of all these things. So it doesn't matter, all these effects happen even in a normal polarization. So then we take back the same situation and we look at the condition that the Fresnel coefficients vary now in the azimuthal direction with reference to the center, and this is, I already showed what happens to this. And now I'm establishing an equivalence for a reason that I'll tell you later. This is what we are looking at in the simulation. A beam is going and then getting reflected. So if you want to measure this, you need to kind of consider a virtual screen here to measure it. So instead of that, I'm doing an equivalence here. This does the same thing as long as the angle of incidence and reflection are taken care. I can even focus the beam and get the same set of results, and it makes doing the experimental process a little more easy. So instead of this, we are going to do this, and the equivalence is established both in the simulation and in the experiment. And so this is what it is, right? Component field. So I send a X-polarized component beam that is going in, and the dominant part of the reflected part in the normal incidence condition is this one, which is the reflected component of the X, this one, and this is superposed with the orthogonally polarized field distribution, which is like this, and vice versa. If I send Y, this is Y dominant, and this is the orthogonal component, which is superposed, which is very, very weak. So all these kind of component field profiles, you get it in the reflected beam, and you put them together, you get the structure of the beam, which looks like this. So when my delta theta E, that means I'm changing the polarization ellipticity at a small angle. So if I make that 0, I get at normal incidence a charge 2 vortex, I will show in a minute. And if I move the ellipticity of the polarization little bit, or the theta E, I'm rotating a little bit, these two charges basically separate in the horizontal direction, and then it separates in the vertical direction. You can see that the polarization distortion is also there, though it is very weak, but it is still there, and your intensity in the orthogonal component shows this kind of intensity structure that is happening in the beam cross section. And you can get the phase structure. This is the charge 2 vortex for normal incidence case, and if you change your polarization orientation in the beam cross section, it separates, and then you can see that it is, these two vortices are non-canonical vortex because this is highly asymmetric kind of a vortex in the horizontal direction and in the vertical direction. So I'll run another movie which shows that what is the dynamics of this pattern. So you can see here that I'm changing the delta theta E. For everything else is fixed. I'm only changing the polarization of the input, and you can see that these two vortices come, join, and then they split in orthogonal direction. And of course, one can plot the trajectory of the singularity. So I take these two singularity points and then see how it changes as a function of delta theta E that is plotted here. And of course, this is in the two-dimensional xy. So this one is here, one is here. They come together, and after making a charge 2 vortex, they separate in the orthogonal direction. We have discussed more physics on these kind of patterns in the paper. I don't have time to go through those things now. So now we'll go to the experimental demonstration. So what we have done is exactly same as what we have done before. Put some polarization gadgets at the input and in the output, and put a camera, and we, instead of diverging, now we are converging it and then getting it reflected, and then measure what is going to be the reflected profile. And this is what you are going to see as far as the reflection component is concerned. You can clearly see that these patterns match with whatever we have shown in the experiment, in the simulation. And this also shows that the single slit diffraction tells you that there are two vortices sitting here, charge 2 vortex sitting here, and 2 single charge vortex sitting at the vertical positions. Of course, we have done the dynamics of that. This is the experimentally measured. So it looks like a nice smiley face. So you can see that these two dark points, you watch that, they will slowly come together, merge, and then go separate in the orthogonal direction. I don't know how clear it is there. So you can see that it is merging, and then it will rotate, and then it will go in the orthogonal direction. So it is happening in the experimental configuration, similar to what we have shown in the simulations also. Okay, now we just went one step ahead and then measured the OAM characteristics of these things based on Barnett's formalism. How much of time do I have? 5 minutes. Okay, I will wrap it up. So this formalism, one can go into this paper, very nice orbital angular momentum flux density formalism is done here. So we have just taken that and then plugged in all our parameters for the electric fields that we have measured for different components, which basically tells you that these are the kind of fields that happens for different input polarization, and we calculate the total OAM flux density as it evolves. And this is what it is. You can see that you can have an orbital angular momentum of charge 2 in the plus component. In the minus component, in which it is coming in, you see these kind of a petal patterns, and here you see that these are two vortices sitting and the orbital angular momentum distribution in the beam cross section. If anybody has questions, we'll look at it. And this basically combines the fact that you have the spin-orbit interaction coming in a very, very subtle way. And this is another video that I'll just quickly show. And then on the left side is the intensity, and on the right side is the OAM density. And you can clearly see that these two vortices coming from essentially infinity, they come close together, merge, and then they separate. And this also tells you how the angular momentum density also changes in the beam cross section as a function of delta theta E. Okay, I'll just summarize it and say that we have taken a closer relook at the fundamental optical process, which is that of reflection of electromagnetic wave at a dielectric interface. And we have kind of seen a lot of interesting things which are topological in nature, and which includes a lot of polarization and phase structure, even if you send a Gaussian beam at the reflection. And in the process, we have done non-trivial unification of your electromagnetic theory along with the newly emerging nomenclature of singularities and orbital angular momentum flux and spin-orbit interaction. All of them are coming together even from a simplest of the optical processes that one can think of. Where do we go from here is that we can clearly see that there is a very, very strong influence of the beam and its characteristics on what is the process that is happening subsequently. And this has led us to kind of looking at singularities, as people have been looking at. The singularities are very, very sharp pointers, and we can use it for many, many applications, and a lot of interesting things are emerging. People are starting to represent, instead of Poincare sphere, they are looking at it as a Majorana sphere, and people have come up with some hybrid Poincare sphere kind of formalism. And you have non-Hermitian photonics coming up. Of course, optical Mobius strip people looked at. Knots, yesterday's super oscillation they talked about. All of them are happening around these fields. And of course, several interdisciplinary areas, including what Ian was telling, microparticles, manipulation of that, microscopy, quantum communications, all kinds of things are going to happen or can happen or is happening as we move forward. And I'll just acknowledge everybody, serve for projects, and of course students are the backbone. More important, I should acknowledge my collaborators, Professor Berry and Bliok and Galvez. I've learned a lot from these people. Of course, I've not met, some of them I've met, others, and they are absolutely inspirational as far as their work is concerned. We are only trying to give an experimental tinge to all their theoretical work in the process. Thank you. I'll take questions.
Thank you, Professor Nirmal, for such an illuminating talk on topics.
More important, this is for students. Yeah, I can take questions.
On topics which many of us use in the laboratory on a daily basis, reflection of light from dielectric surfaces, but on a new light. Your talk was very interesting. So, question?
Professor Aharonov.
I had a question about the formalism itself. I mean, at an intuitive level, to say that you have different angles of incidence at different points on the beam and therefore different Fresnel coefficients is a nice picture. But for actual calculation, if you do a complete Fourier decomposition, no real space would emerge at all. No? For each K would get its Fresnel coefficient, and then you would get the real space picture by putting it together again. I would have thought. Huh?
No.
Oh, okay. So
No.
then maybe I have not understood the formalism. So you do use a real space picture.
Yeah.
Okay,
Completely.
fine.
Yeah. That is why we had to kind of develop a completely an independent formalism, because existing formalism do not look at this in a careful way. So we'll have to look, because we, see, the whole thing, I'm an experimentalist. So we did the experiment, saw some weird things. So we went back and started doing the theoretical formalism to see how do we kind of understand this whole thing.
Another question.
Yeah.
There is a question from the back, then we'll come to you.
Yeah.
Thank you for the talks. So, I have a very simple question. Like, if I understood correctly, so you have a Gaussian beam which is reflected,
Yeah.
and it develops a orbital angular momentum.
Yes.
So, sir, if the incident beam is linearly polarized,
No, circularly polarized.
so if it's linearly polarized, we won't have that feature. Okay. So, how is the angular momentum conservation working here? Like, so
Some part of spin gets transferred to orbital.
okay. Thanks.
Yeah, that is a part of spin-orbit interaction, right? So the spin and orbital angular momentum degrees of freedom are coupled. So you touch one thing, the other thing, something else happens.
Will it develop the donut shape as well?
That is what I showed, right?
So Gaussian beam will become a donut?
Of course it will become.
Okay.
That's what I showed. You didn't see those things?
A little bit confused. So, yeah.
No. Okay, we'll look at it again. Yeah. You can look at the papers that we have published. Yeah.
So are you saying that? No, wait a second. There is a question here. Then come to you.
Sir, initially we have a Gaussian beam that you focus, that reflect from the dielectric surface.
One can focus, but one doesn't have to focus.
Yeah.
The divergence is good enough.
You have shown both the situation.
Yeah, of course. Yeah.
So that reflect from the dielectric. Initially we have a Gaussian, so we get a HG type pattern, HG beam, first order HG beam.
No.
After the reflection, you have shown the. So there is a two lobes and there is a singularity axis.
No. Two lobes are not two independent lobes. Two lobes are connected lobes. That you have to look at it carefully.
That two lobes are this.
If this is what you are saying, but there is a connection here, right?
Yeah,
it is not two independent lobes.
Singularity axis.
That is why you see a singularity. That means the field is varying uniformly in the cross section of the beam.
So the Gaussian shift that you were showing, in terms of lambda, how large is it?
In terms of lambda?
Yes, sorry, it was in millimeters. So what is the
it all depends on the size of the beam that you come in with, right? How much of spread in k vector that you have done.
Right.
So that will depend scale accordingly. Okay. I think in one of the graphs I have given how much is, here. Some scaling is there, right here. So this is about, let us say, if I have I think 2 millimeter beam spot size. So this is about half a millimeter. So it's about 1/4 of it. But we never optimized for large beam shift and all the thing. All I want to say is that the beam shift that one talks about is already there in the beam the moment you reflect it. One doesn't have to do anything special. That is the point.
And so the wavelength of the light?
632, helium neon laser.
Okay, thank you, Professor
Thanks.
Nirmal, for such a nice talk. And